Are there questions coming from any source? Yes, please, do it. Tell us who you are before you ask a question.
My name is Detlef Hohl. I'm with Shell Research. I have a question concerning the application domain. You're always focusing on the electrons, but you showed a problem. In fact, even in the pharmaceutical example where the hydrogen, the protons, play a very important role. They are a quantum particle. The proton hopping problem in water is significantly impacted by the quantum nature of the proton. Can't you incorporate that into your quantum computing scheme?
It's certainly possible. Do you want to comment on that?
Yes, so I think I hinted at it. We have an algorithm where, because in the end you are interested just where are the protons, but the electrons tell you sort of where they move. So we sketched out an algorithm where there's also treatment of the protons, but sort of they are not quantum mechanical, they're just classical around, and then you find some unitary formulation of Newton's equations sort of to make it fit. And then sort of the interaction is between the two, and the forces, you solve the electronic structure problem, which then sort of impacts the nuclei, and sort of you go back and forth in this loop, and then you do thermodynamics on
the standard approach is path integral molecular dynamics, right? That's been done many times. Is that equivalent what you're doing?
Yes, it's sort of aiming at to do the same thing.
Looking for anyone else? Cécile, do you want to say a bit more about how you see the time frame for these fault-tolerant devices impacting applications?
Yes, so everything has been accelerating, and I'm not exaggerating. I know that everybody's telling you the hype is coming, but we've been seeing such fast progress on fault tolerant. This idea that the first useful cases are going to require 100 logical qubits. I mean, you actually showed how that was reduced massively in the number, well, in time and also in the resources that are going to be allocated. So everybody's saying the 100 logical qubit machine is going to be ready for 2030, but we need work like the ones that you're doing on the algorithms, and we might actually have algorithms that are going to require 50 logical qubits, and the 50 logical qubits are coming in 1 or 2 years. That's why I always say that in the case of quantum progress, we need both the hardware development but also the algorithm, and it's very critical that we see more application work being done, because the timeline could actually be shorter in terms of which algorithms and when can we implement them. I don't want to give a date because I don't know a date, but it's already quite, we've seen FTQC dramatically get closer. Everybody's quite comfortable saying, 5 to 8 years, the machines are going to be there. Now we're going to see what algorithm brings us, and it might reduce even closer the useful machines.
Right. And Gian-Luca, from you, in terms of the pharma industry as a whole, were you talking on behalf of them all, or Boehringer Ingelheim? In other words, what's the uptake of this technology looking like currently across that sector?
I think currently, because there is no competitive algorithm, sort of uptake is slow, I'd say, because there's no need to use the algorithm. You're not competitive if you don't use a quantum algorithm. I think our approach is that if you are not partaking in the field, you cannot shape the field to go towards the things you want to do with the machine. I think scientists are good at working in their boxes, but they also need to tell someone, okay, here's a reward that you can sort of migrate towards. So if you could do this, it would be very valuable. And giving the field direction and shaping what things are being developed or how sort of application is viewed in the field, I think is very valuable. And this is sort of part of our job to show, okay, maybe this is good, but maybe not good enough. And if we could do this, this might actually be an application in the pharmaceutical industry.
And from your presentation, the kind of entities you collaborate with, can you summarize those?
Yes, so we have, I mostly showed collaborations with industry partners or startups with Website Quantum, QCware as well. So they are sort of quantum players that either build a box or want to provide services for one. But we also do projects with universities like Yale and University of Toronto, where I think the more academic part of the portfolio sort of happens. For example, the development of the algorithm with where the nuclei are also treated as that one. I don't think this is research that can happen in industry, or you need some academic part of it. But I mean, the lines are fairly blurry in the field anyhow, because sort of most of the academics, a lot of academics have migrated either into the big players like Google or into some startup. So even the work in industry is, I think, quite academic from time to time as well. But it needs a little bit of both to make these things work. And there's still a couple of orders of magnitude to shave off, but as I think experience shows, we've managed to shave off a lot to here. It's even a wonder that we got where we are today. We just have to continue the track record.
The same question for you, Cécile, in terms of who...
I think there's also a
Is there someone over there? Oh, I beg your pardon. Please, let us know who you are.
Hello, my name is Patricia. I am from Berkeley National Lab. And my question is regarding you. In one of your slides, you show a humongous, I think, cryogenic refrigerator to fit all these qubits. And I was wondering, what is it that requires you to have this humongous thing to power quantum computing? I think it's related with the power capacity of the cryogenic refrigerator. But then when you look in the future, is it because you're planning to put all the control inside of it? Is it because of the multiplexing? Is it because you're using cryo-CMOS for, what is it that is necessary to have this gigantic infrastructure?
That's an excellent point. So my specialty is superconducting, and so the fridge I can relate to. There is a number of technological innovation that still needs to happen as we scale up those machines. In Alice and Bob, we're quite lucky, but we made it lucky, that our 100 logical qubit is going to fit inside of one current cryostat. So we don't need to start interactions between the cryostats. But all of the other technologies are going to need to have fridges that talk to each other. And so quantum memory needs to be improved. We also need more cables inside of a fridge. So that's where you see more flexible cables being done, bigger fridges, obviously. And as we scale, we're probably not going to be having those. I don't know if all of you have seen a cryostat. It has this psh, 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 psh. If we're going to have hundreds of those, they're too noisy for our qubits, so we're going to need to go into a liquefier kind of cryostats. But those innovations are being done by all of our enabling technology providers. They all know that that's the directions. The roadmaps that we publish, it's not just to make a marketing ploy that we know how we're going to do. It's also telling all of our suppliers, hey, we're going in that direction, so we need you guys to make sure that it happens. And the way we're seeing it, our enabling technologies are definitely moving in the right directions. But yeah, there's a number of innovations that hardware is going to be super interesting for the next few years.
Great. Well, I think there aren't any more questions coming, and it's a moment when we can draw the event to a close. I want to thank my fellow speakers for contributing to this, and also for you for attending. Thank you all very much indeed.